Today we're going to be talking about Assistive Gym. So Assistive Gym is the physics simulation framework that we're going to be using throughout the semester. And it's going to allow us to simulate robots interacting and assisting with people. So here's just some different examples. The first one was feeding assistance, and this one here is dressing assistance. So today we're going to be talking about Assistive Gym, how it works, how you can use it. And to start off with, I'd like everyone to actually open up a Google Colab notebook. So we're going to try to do something a little bit different during this lecture and make it a little bit interactive. So we've built a Google Colab notebook that you guys can use to run code that aligns with the lecture. And so if you just open up that link, what you're going to be looking for is something like this. Right? So if you've seen Colab before, this should be pretty familiar. And the most important thing that we do before we start the lecture is have everyone hit this little play button. So the very first code segment that says install Assistive Gym, just hit the play button on that. It's going to take a few minutes to install. So we're going to have it install while we go through the rest of some of the other slides in the lecture. And then by the time we need to use this, hopefully everything will have been installed and ready to go for us. All right. And so you should see something kind of similar to this, my screen, that yours might have a white background when you open it. And it's just that first code segment. You want to hit play, and then that's it. We can go back to the slides. Any questions on that? All right, so today we're going to be talking about, again, Assistive Gym. It's an open source physics simulation framework for simulating assistive robotics or assistive robots. And the first thing to really talk about is why are we interested in physics simulation? Despite the fact, obviously, because it's an online course this year, physics simulation makes sense because we can all use it. But outside of that context, what is interesting about physics simulation? Well, it turns out that the field of physically assistive robotics has a number of challenges that come with it. For example, probably the largest one that's been the biggest barrier of entry into the field of assistive robotics is high costs. Like the types of robots that can provide assistance and conducting human studies and such is all very expensive to do these kind of things. In addition, there's an element of risk anytime you have robots coming into close physical contact with people. We never want robots to accidentally hurt someone, right? So there's risks inherent with human-robot interaction. And then lastly, it's just slow to collect data with real robots. And this is especially true when you have robots interacting with people, such as in assistive robotics. And so taking all of these in combination, it can be sometimes pretty challenging to work with real robots that need to interact with real people. And so that physics simulation allows us to overcome a lot of these issues. And this isn't specific to just assistive robotics. In fact, anytime you have robots interacting with people, you'll oftentimes come up or interact or have issues with these same components of costs, risks, and slow data collection. And so that's really what simulation is helping us overcome in some cases. So Assistive Gym, which we're going to be looking at today, consists of a few components. First, it's built on the PyBullet physics engine. We're going to be talking about this engine just a little bit briefly throughout these slides. We're not going to talk about any of the equations or algorithms used to run physics engines, but if you are interested in a course that talks more in depth about physics engines and physics simulation, there's a course called Computer Animation by Si-Hoon Ha, Professor Si-Hoon Ha here at Georgia Tech, and that's a great course to take if you're interested in specifically physics engines. Now, Assistive Gym connects into what's called the Openaigm Gym interface. We're also going to be talking about what this is a little bit throughout these slides. It's essentially just an interface that provides kind of a uniform set of commands for interacting between robots to interact with these simulated robots, essentially. And then with Assistive Gym, we're able to perform real-time simulation. What that allows us to do is train robots in the cloud using hundreds of machines or running thousands of simulations in the cloud, but then download what has been learned and test out these robots in real time on our own laptops or machines. So Assistive Gym uses the PyBullet physics engine. What this is an open source set of Python wrappers for the Bullet physics engine, which is written in C++. So PyBullet includes both rigid body and soft body position-based dynamics. So rigid bodies are things like robots, where you can think of them as like made of metal, right? They're connected by joints. And then soft bodies, things like cloth or rope, things that are very deformable Liquid could be another form of a soft body. With this, PyBullet provides also both CPU and GPU rendering support. Now, throughout most of this course, we're probably going to be just using CPU rendering. That's especially true if you're using Google Colab. But if you do install Assistive Gym on your own machine, and we do encourage you to do so at some point for your projects, you'll be able to use your GPU on your machine if you have one. And the last part is that we're going to be looking at a little bit of code throughout these slides. Now, most of the code that you're going to be using is going to be actually interacting with kind of custom functions that we've built in Assistive Gym for controlling robots. Oftentimes, you won't have to interface or write code directly for the PyBullet physics engine. But if you ever come into a scenario in which you do, there's this helpful kind of quick starter guide for PyBullet that provides a list of all the functions that PyBullet can use, that you can use in PyBullet directly with the physics engine. So where is Bullet physics used? In fact, this library, Bullet physics engine, has existed since around 2003, I believe. And so it's been used in a number of both films and games. Some films you might be familiar with is, for example, How to Train Your Dragon, Megamind, and Shrek. And some popular games that the Bullet physics engine is used in is things like Red Dead Redemption, Grand Theft Auto 5, Rocket League. Now, PyBullet, as of kind of recently in the last, 5 or 6 years, has been gaining interest in the field of robotics. In fact, the lead developer and kind of creator of PyBullet, Erwin Koemans, is now working at Google Robotics, and he's been doing so since 2014. And since then, there's been a number of different, I would say, papers and research projects that have been leveraging PyBullet to train or simulate robots, and then what's learned in simulation is then transferred over to real robots that perform real tasks. For example, picking up objects out of a bin, or teaching these quadruped locomotion robots to walk or gallop. So we just finished looking at the PyBullet physics engine. It's been used in a number of different examples, both movies, games, and more recently in robotics. Now, the other component of Assistive Gym is the Openaigm Gym interface. And so what this is an open source toolkit that provides both, well, a set of collection of tasks and environments. But what we're most interested in with this Openaigm Gym interface is that it provides kind of a unified interface for developing and comparing different control algorithms, as well as how do you control different agents or robots. And I think up here we should see a couple of different videos or short animated GIFs of different things that you might encounter in Openaigm Gym. So you use the exact same interface to essentially do all of these different things. So a swinging pendulum, where the action is just swing left or swing right. The Atari game, where the action is move the paddle to the left or right. Right? You have these different animated characters that can run around different obstacle courses. A fetch robot, which is the goal is just to pick up a block and move it around to a different location on the table. Or again, this animated human character here, where the goal is to run towards different locations in 3D space. Right? And so the same, essentially you can write very similar code to control all of these different examples by using and interfacing with the Openaigm Gym. And as an example of that, here's just some code examples. So we're going to be in this course using Openaigm Gym. So hopefully throughout the course, you'll get very comfortable with interacting with this type of Openaigm Gym interface, as well as the simulation environment. And so here's just a quick couple line code example in Python of how to actually use Openaigm Gym. So the first is that you import Gym, and in this case, Assistive Gym. Then we're going to create a new environment. So you're going to say gym.make, and then you're going to specify the name of the environment. In this case, it'll be feeding Jaco. And then that's going to create an environment that looks kind of like this. Right, we've got a human sitting in a wheelchair and this Zackory robot mounted on the wheelchair holding a spoon of food. Then we're going to say environment.render. That's going to create, if you install Assistive Gym on your computer, you will use environment.render. If you're using Google Cloud, you will not. Environment.render is going to create a window on your computer, which will show this simulation. We'll then reset the environment. So environment.reset will set it back to its default state. And then we're just going to have a loop that loops over all of the time steps that we want to simulate. And for each time step, we're going to first create, in this case, we're just going to create a random action. You can kind of think of this as like a vector of a bunch of different numbers. And each number specifies how fast or how much each joint on the robot's arm should move by. And then we're going to feed that action into a function called environment.step. And that's going to perform one step of the simulation. Right? So it's going to take this action, it's going to run exactly 0.1 seconds of time in the simulation. And then after that, after it's done simulating 0.1 second of time, it's going to return back to us an observation. You can kind of think of this as like an observation of what the robot sees in the environment. Things like how much force the robot is feeling on its fingertips, what are the current joint angles of the robot's arm. If the robot has a camera, that could also be included. An image from the camera could be included in this observation. And you also get, the other important thing is you'll get a reward number. And so this is a number specifying how good the robot is doing, right? You can think of this as, in the example of feeding assistance, if the robot gets food into a person's mouth, it'll get a high reward for doing so. And if it drops the food on a person's body, that's a very bad reward, right? Or it'll get a very negative reward, indicating that it has done something bad. Any questions on that? It's kind of a very quick code example of what this Openaigm Interface actually looks like. And of course, throughout the lectures and throughout the semester, you're going to get hopefully a little bit more familiar with doing these kind of things on a regular basis. Environment, in particular, here is an object. It's an object. You think of it as the environment object, and that environment object has a bunch of different functions you can call. One of them is the reset function, which resets the environment back to its default state. Another one is the step function, which, as you specified, it takes in an action for the robot and then will perform one step of the simulation. After the step function finishes, it will return to you 4 different things: an observation, a reward, a value that specifies whether the simulation is done or not, and as well as some extra information which may or may not be empty. Yep, so once this step function finishes, it'll return to you a bunch of different things. Yep. Thank you. Any other questions? If not, we will dive into some of the key features of Assistive Gym. So Assistive Gym supports 6 different assistive tasks currently. This includes itch scratching assistance, bed bathing assistance, feeding assistance, drinking assistance, dressing, and the last one is going to be arm manipulation assistance. And so these are the 6 different tasks or environments that come included with Assistive Gym and that are available already pre-built. Now, we also have 6 different robots that come with Assistive Gym. The first 4 are the PR2, the Zackory robot here. This is the Baxter robot, and this one here is a Sawyer robot. And there are 2 additional robots that have been added more recently, both the Stretch and the Panda robots. And the reason for these robots in particular is that within the field of assistive robotics or human-robot interaction, these are some of the more common robots to find interacting with people. With Assistive Gym, there's also human models, both for male and female human models. Each of these models has 40 controllable joints, things like a 3 degree of freedom neck and head, a torso with a bendable waist, right, 7 degree of freedom arms, as well as legs and actuatable feet. And another interesting aspect of Assistive Gym is modeling realistic human joint limits. So on the left here was an example of non-realistic joint limits. and on the right is an example of realistic joint limits. But it's actually a very easy concept to try out yourself. So I'd actually encourage everyone to try this out right now. Put your hand in front of your body and bend your elbow. And what you'll notice is that you're probably able to bend the full range of your elbow, right, all the way from straight arm all the way to fully bent. Now try to put your hand behind your back and do that same bending motion. And what you'll notice is that you're probably not able to bend your elbow nearly as much. And it's this kind of concept that's been incorporated into Assistive Gym, where essentially the range of your motion, the range of your joints changes depending on the pose of your arm or your limb. Any questions about that? Kind of just a really quick, simple example of something that you probably take for granted, but when you have to simulate people, it's something that shows up quite easily in a number of different scenarios. All right, another thing that you'll encounter with Assistive Gym is robot base positioning. So where a robot is next to a person actually can make a pretty big impact on how well it can assist people. For example, if the robot is really far away from the person and can barely reach the person, it likely won't actually be able to help a person, right? Similarly, if you put the robot right on top of the person, it might be kind of uncomfortable both for the robot and the person. And so based off of this concept, there's something that happens in the background. You'll probably never have to deal with this, but it is happening in the background, is that when we create an environment where the robot is positioned next to a person is actually optimized. It's doing so, it's done using an algorithm called joint limit weighted kinematic isotropy. You don't really need to know what this algorithm is or how it works, but essentially it's just finding locations near a person for the robot in which the robot has what's called a high amount of manipulability. So it has a lot of motion around the person's body, essentially. Another thing that comes with Assistive Gym is human preferences. So when people are receiving assistance, they generally prefer not to have water spilt all over their bodies or for robots to apply large forces or large pressures onto their body. And so based off of this concept, we've included a set of human preferences in Assistive Gym. And these preferences impact a robot's received reward, right? So if a robot spills a bunch of water on the person's body, the robot will get a negative reward. It's essentially we will penalize the robot for doing so. And hopefully the robot can recognize that it has made a mistake and learn to or recognize to do something better or choose a different action in the future. So those are some of I would say the basic set of features that come with Assistive Gym. And so at this point, let's actually start to test out Assistive Gym in Google Colab. So the first section is section 1, getting started. What we're going to be doing is we're just going to simulate a Zackory, in this case, a Zackory robot, providing feeding assistance to a human sitting in a wheelchair. And so if we go back over to our Google Colab notebook, what we're just going to be doing is running all of the code segments here in this first section. So we're going to do a bunch of imports, right? And then this first section, again, we've seen this before, environment equals gym.make, so that's going to create our environment for us. We're going to set a random seed value. It just seeds the random number generator for us. And then we're going to create a camera in the environment, and this camera is going to allow us to see what's happening during the simulation. So as it's simulating, this camera is going to be taking photos for us, and then we're going to render that in Google Colab so we can see what's happening in the simulator. This is something, by the way, this setting up a camera is not something you would have to do normally if you install Assistive Gym on your own computer, because you'll have a window that pops up that shows you the entire simulation as it's running. So after that, we will run this code segment, and this is actually going to do the simulation of the environment. So it's going to reset the environment, and then it's got this while loop. Well, essentially it's going to continually simulate each step of the simulation until it has finished the simulation. And in a sense, it's going to be about 20 seconds of real world time, right? So it's going to take 200 steps, where each step is 0.1 seconds of simulation time. Right, so we're going to call environment.step again, which we've seen a few slides ago, and then we're going to get the camera image from the camera that we had created, and we're essentially going to create a video out of that, right? So we're going to get a bunch of images and we're going to splice them all together to create a video, and then it's that video that we're going to show. So at this point, it's now done, and if we run the next two segments, this next one is going to turn all of those camera frames into an animated PNG file. And then this last segment is going to actually visualize that file in Google Colab. Any questions about what's going on here? Hopefully it'll show up soon once it's done compiling the short animated PNG. If you have Google Colab open, you're welcome to run them during the lecture. If you don't, that's why I'm showing them, so you can see what would happen. So you don't have to run these, but if you'd like to follow along with the lecture. Yeah. We're going to be doing this more throughout the semester too, using Google Colab for different lectures. Of course, if you let us know if you like this kind of notion of making these interactive lectures where you can run code during the lecture. If you don't like it, we can stop it. It's something we're trying. So the question is, A, is the robot taking random actions? The answer to that is yes, it is. And if so, why is the robot not moving around more rapidly and potentially hitting the person, these kind of things? The answer to that is it could, if the random number generator created these types of random motions. What happens is, at least in this case, is that we're seeing that it's, for example, maybe in one time step it'll move to the left, and the next time step it'll move to the right. And so when you keep doing that over and over again, you essentially don't see much movement. And if you want to, it's actually not hard to break this or to try something a little bit different. So we don't have to take random actions. And if you wanted to, you can actually change this. So you can say something like action equals np.array. Or actually, let's change this. Let's just say np.ones. And this is, and then specifically, it's the number 7. That's how many joints are on the robot arm. And so this is going to create a vector of 7 numbers, or seven number ones. And then if we just, in our step function, if we just say action here, instead of creating a random action, now we have an action of all ones. What that's going to do is essentially move all of the joints, you think of them clockwise. So it's going to move all of these rotary joints clockwise, all at their maximum speed. And if we were to simulate that and then step forward, in order to resimulate that, you have to start over at the beginning, recreate the environment, reset it. If we run through this, it'll take a little bit of time for it to rerun the simulation, but you should see something much more extreme where, for example, the robot might just move its arm all the way down into the table, right? Something like that. Or it might move its arm all the way up into the sky. One of these two examples might happen. Yeah, and so it happens to be that the reason why it's not moving around more drastically is just because of the random number generator and how it's picking actions. They might be essentially canceling themselves out after a couple of time steps. Yeah. Yep. Good question. There we go. So yeah, in this case, it lifts its arm all the way up. Yep. And so that's what it ends up looking like. Yeah, so you can see something completely different. And then here, it's probably going to hit the person. Yeah, run into their head. Maybe not safe, but luckily in simulation, it's okay. There we go. So yeah, just a quick code change here. We can get completely different actions from the robot. All right. So let's move on. So there's also some advanced features that come with Assistive Gym. And so we're going to look at some of those, some other cool things that you can do with Assistive Gym. In fact, in your project, your midterm projects, these are some of the things you might be interested in using. So one of them is their support for multiple robots. So here is an example of 2 different stretch robots. We have each of them holding on a different side of here is a fabric hospital gown. And we can control each of these robots independently to try to have them help pull this gown onto a person's upper body. We can also simulate 3D human meshes. So in this case here, you're going to see this is what's called a capsulized human. It's kind of an abstract representation of a human. There's a number of benefits from using this type of human. A is that we can move it around. We can connect all of these independent capsules, or essentially cylinders with 2 spheres on the end. So we can connect each of these capsules with a joint and then move these joints to move around the different body parts. There's also each of these are very fundamental shapes. And so that also makes the computation of collisions a lot easier. So it's a lot easier to detect if something has collided or is intersecting or penetrating a cylinder than a full 3D human mesh like what we see here. So this is a full 3D human mesh. We can also simulate these in Assistive Gym. And there's Google Colab examples of how to do this. But what you will, now the nice thing about them is that you get more like this human morphology, right? It matches what humans look like a little bit better. The downside is that these are static models, so you can't move them around. Once you create them, you can create them at different poses and such, right? They can be leaning forward or leaning back, or they can be looking in different directions, and you can change where their arms are posed. But once you create this 3D human mesh, you can't move it anymore. It's fixed there and it's static. So that's one of the downsides of using these mesh models in comparison to a capsulized human. But if you're okay with people holding static poses, not moving around, then this is an option. Another thing which we briefly mentioned at the beginning of the course was this iGibson thing. And so Assistive Gym is integrated with the iGibson framework, and that allows us to simulate, or iGibson in general simulates photorealistic home environments like what you're seeing here on the left and right images. And so we can connect Assistive Gym with that, and so now we can be simulating humans and robots in these environments where the robot can, for example, drive up to a person that's sitting in a chair. If the robot drives too far, it could push the person off of the chair, and the chair could fly around, these kind of things. So all of the objects in these environments are also interactive. So you can push the tables, the different things on the tables can all be pushed around and moved. Even things like the refrigerators, the microwave, all of that stuff can be moved. So it's a very interactive environment. And this can also be simulated in Google Colab, although you'll notice that it can get a little grainy. The text, it's not as high quality as you would see if you install Assistive Gym on your own laptop or computer at home. Another cool thing we can do with Assistive Gym is virtual reality. So we can actually use virtual reality to bring people into these simulated environments to take control of these simulated humans and start interacting with virtual robots. And so that's what we can see here. Here are 3 different views of what we call Assistive Vr Gym. So we have a research paper on this concept, but we're able to take real people, put them inside of a virtual reality environment and bring them into Assistive Gym where they're now controlling the body of a simulated human, and they can move around and interact with the robot, and the robot can try to assist them. So that's another cool thing we can do with with Assistive Gym, is combine it with virtual reality. Yep, and so as Charlie mentioned, one of the really big benefits of Assistive Vr Gym, or VR in general, is that it allows us to start to test out these robots. So with the simulation, we can train robots to interact or assist people. And by using virtual reality, we can start to evaluate these robots with real people before having to deal with the complexities of using real robots. If the robot makes a mistake, right, we don't have to worry about a person getting hurt. There's no risks inherent there's no real robot, so the person can't get hurt from this interaction. So it allows us to really test out what robots have learned in a very safe environment. It's a little bit faster to test and do these evaluations than working with real hardware. So as Charlie was mentioning, there's a number of benefits that come with virtual reality and why it's an interesting component. So let's now look at different ways that robots can provide assistance to people. And the first thing we'll look at is how can robots provide assistance to a person who's holding a static pose, so the person isn't moving. And so here's kind of a video of some different examples of what robots have learned to provide assistance to people. In this case, here's a soy robot trying to clean off a person's arm. Here's a Baxter robot trying to feed someone. And here's a PR2 robot that's trying to pour water into a person's mouth. And I can play these again for you. You can see them again. So this is just what robots have learned from simulation in terms of providing assistance to statically posed people, so people who are not moving around in simulation. And so this begs the question of, well, how do we do this? How do we control assistive robots in simulation? And so this is actually going to bring us to kind of a brainstorming session, which is, so it requires some feedback from all of you, is how do we control robots? What are some different ways that you can think of to control robots? And you don't have to specify an algorithm. If you want, you can just discuss an idea, like kind of abstract idea of how we could think of controlling a robot. And if there's an algorithm that we know of, we can mention the name if that matches with what you're talking about. So what do I mean by control robots? One way to ground this into something you've already seen is in Google Colab, we have this action here, right, that we're feeding into the simulator. How do we know what action to take, right? We get an observation. So for example, maybe the robot can see where a person is at. They can see the person's mouth. They can see where their spoon is at. They can see the Euclidean distance between the spoon and the mouth. How do we pick an action to move the spoon closer to a person's mouth? Yeah, so having feedback is especially important, and this is especially true when interacting with people, right? We don't want the robot to push too hard into a person. If it doesn't have a way of feeling how much force it's applying, it could hurt someone, right? You could think of like pushing into the face. The robot doesn't know if it's pushing really hard or not unless it has some sort of force sensor. So one I'll provide, if you guys would like, is a technique that uses prediction, right? So we can actually predict into the future, if I were to take this action, what would happen, right? You do a bunch of different predictions for different actions, and then you choose the one that you like the best. And this is a technique called model predictive control, which does exactly that. You predict into the future what would happen if I do this or this or this. What happens if I move the robot to the left? What happens if I move it to the right? And then you try a bunch of different things, and you choose the one that works the best for you or for the robot. Good point, Tele Operation. So yes, the ability for a human to control a robot, Tele Operation. We're actually going to see an example of that here in the lecture. One really simple example of that is you could just think of, you can literally just have a joystick that moves each of the joints on the robot's arm, right? So if you move the joystick to the left, it'll move the arm out. If you move it to the right, it'll move the arm in, these kind of things. And it is a very powerful concept that we will dive into. Any other thoughts? There's a ton more, but there's a pretty good list already. We'll see some more as well in this lecture of other ways to control robots. Yeah, so shared autonomy, definitely. The ability for humans to do some of that control and for robots to automate other things. An example of this in assistive robotics is that you can have, for example, a human drive the robot up to a refrigerator, and then the human tells the robot to automate the process of actually opening the refrigerator door, right? Let's actually talk about Tele Operation. In the Google Colab notebook, if we open that back up, section 2 is all about how to teleoperate robots in Google Colab. So what this is doing, there's a bunch of code here. It's not actually too much. There's a chunk of code that really just creates these sliders and buttons. And what we're actually looking at here is this is called essentially end effector teleoperation control. And so the end effector is essentially the robot's gripper, which is holding, in this case, a spoon. And what we can do is move these sliders. Each one represents an axis of movement. So you've got like the z-axis, which is up and down. The x-axis is kind of left and right. And the y-axis is going to be in or away from the person, right? So what you can do is move these sliders, say, oh, I want the robot to move the spoon up in the z-axis all the way up into the sky. And then we can hit simulate. And then after a few seconds, we'll actually see what that looks like. So here, there you go. We see it lift the spoon up. We can do the exact same thing in the opposite direction. We can tell it to move the spoon down along the z-axis. Is everyone able to see what this is doing? So here it's starting to move back down. And if we simulate it again, you'll probably see that move even further down. There we go. Yep, this is a really good point. So with this in particular, with a lot of the Google Colab notebooks that I like to design, I like to obviously run them all to make sure that they run. And then all of the outputs, I will usually save those outputs and then give you the whole notebook so you can see what the outputs look like, even if you don't run anything. Right? You can just scroll through the notebook to see everything that it's going to create. Right? And then when you run it yourself, you should hopefully see the exact same output. So that's how I like to structure these notebooks. If you guys don't, when you open this notebook, you will create a copy of it. So if you run things, it will not affect the original notebook, right? So if you run a bunch of things or make changes, those changes are local to you, and it will not affect anyone else. It's a really good point. Yes. So all of this is local to just you. It's all private to you. Yep. So anything you run, anything you simulate, anything you change will not affect anyone else. Anyone have questions on this notion of Tele Operation? Any questions of how this works? So when you have these sliders and they're moving around the end effector, but the way we control a robot is we actually control the joints, right? So we bend the elbow, right? We bend the wrist. We don't actually move the hand around directly. And so what we do is when you move that slider, you're telling the hand to move to the left or move to the right. We use a technique called what's called inverse kinematics, which says, oh, I want my end effector to be at this location. What do all of my joint angles need to be set at to move my end effector from where it's currently at to this new location? What we're going to be looking at is this line right here. So it says environment.robot.ik, standing for inverse kinematics. And that's what's actually computing so given I want to control the robot's right end effector, env.robot.right end effector, and I want it to move to this new target position and keep its same starting orientation. Right. And then the other things you don't have to worry too much about. They're kind of just boilerplate stuff. It's really these first three arguments that are really important. I want to control the robot end effector, and I want it to move to this target position, 3D location, X, Y, Z, and I want it to have this orientation. You could think of it as roll, pitch, and yaw, but it's actually in quaternions, but that's something we'll just brush past for the moment. And so all we do is all these sliders are doing down here is they're changing this target position. They're changing the X, Y, and Z values in that target position. So anytime you change the slider, it changes this target position, and when you hit simulate, it'll simulate 10 time steps of the simulation, trying to move to these new joint angles that were provided by inverse kinematics. Correct. Yes, so once you hit simulate, it's going to keep the simulation at its current location. You'll simulate and it'll move the robot from where it's currently at to its new location, right? You're correct. It's not going to restart the simulation. And so that allows you to kind of like connect these motions where you can have it move up and then it'll move down and then to the left and then to the right. It won't always start back at the center. What you're encountering, so as an example, so if you see a figure here, it's moving downwards. If I move the slider all the way back up, so I want the robot to start moving up, what you will encounter, if we simulate this again, is the robot will probably not move that far up. Yeah, so you see right here, it kind of, what's actually happening here in physics terms is velocity and acceleration. So the robot is actually accelerating down, and we just told the robot to start moving upwards, but it takes time for it to slow down, right, to decelerate, and then start to accelerate back up. And so we only simulate a couple of time steps. And so those 10 time steps is essentially all spent changing the acceleration of the robot. And if we simulated another 10 time steps, we should then see the robot start moving upwards. There we go. Yes, so sometimes if you change the robot very drastically, from moving all the way up to moving down, you might also encounter acceleration and velocity. So you might have to simulate a couple more times to see that motion, just because it takes time for the robot to change its acceleration. So the question is, why does it, if you set the y-axis all the way to its maximum value, why does it not just keep moving and moving and moving closer to the person? And the answer to that is that these are actually offsets from the starting position. So when we initially created the environment, the robot was at some starting position, and these sliders are offsets from that starting position. Yep, good question. As an example, if you set all of these back to 0, what you will see is the robot moves back to its starting position. Hopefully that will clarify that a little bit. So what Charlie was referencing is, can we, instead of having these sliders be offsets from the starting position, can you have them be offsets from the current position of the robot and effector? And the way to do that is to use a function. You actually have to change these. So it's these slider functions, which are adding the slider value to the starting position. And that's what's being set to the target position. And instead of having the starter position, what you essentially need to do is call a function called env.robot.getPositionOrient. And we can talk more about this in future lectures of what are the kind of functions that are available for robots and for humans and these kind of things, how to control these different agents or move them around. But if you do this and then env.robot.writeEndEffector, this will provide for us the position and orientation of the robot's end effector that it's currently set at, right? And so if you were to change the starting position to something like get the position orientation, getting that position, if you were to use this position instead of starting position, then you would see it. If you change this slider all the way up, it'll keep moving up, and it'll just keep trying to move up and up and up. Right. Any questions on that? It's a really good exercise there. All right. We're actually getting close to the end of the lecture, which is just fine because the rest of the lecture is looking at, so far we've seen some more essentially human control. How do humans or ourselves control these robots manually using like a technique called Tele Operation, or for example, using random actions. And the next thing that we could look at would be, how do we have robots learn to provide assistance on their own, right? Which would bring us to a topic of machine learning, or in this case, reinforcement learning. Now, we're not going to talk about this today because we're pretty much out of time. But in a future lecture, we're going to actually talk about reinforcement learning in more depth, both how it works, how you can train robots to learn to provide assistance on their own. They will learn how to do this without having to be told how to provide assistance explicitly. And as just a very quick example of this, in this Google Colab notebook in section 3, you're welcome to do this outside of the class. You can run these last few code boxes in Google Colab, and what you'll see is the robot is using a pre-trained controller that it has learned to, in this case, perform a bed bathing task. Where here, the robot is going to use this controller that it has already learned to wipe off the arm of a person right here. And if I kind of zoom in on this, yeah. And so you'll see that it kind of performs this motion up and down along the arm to clean off as many blue circles or blue dots as possible. We'll be working a lot more in Assistive Gym throughout the semester, so of course you'll hopefully get a lot more familiar with it as we progress. But this is just a very quick intro into what you'll be experiencing throughout the rest of this semester.